Okay, hi everybody. So, we're getting close to the end of Physics 232. Really, one of the last topics that I want to just introduce is Monte Carlo methods. Ultimately, what we'd like to be able to do is to use these Monte Carlo simulations to understand something about the behavior of a physical system. But before we get into that, what I want to show you is how they can be used to do some calculations that might be difficult to solve analytically or maybe impossible to solve analytically. And so a good example of that is integrals. So there are lots of integrals where there are no analytical solutions, and we have to rely on numerical methods to evaluate the value of a definite integral. Um, so let's see how the Monte Carlo method works. So first, just a general comment that they're useful for numerical integration. And we're going to see an example of that today in this video. So what the method does is the Monte Carlo method uses repeated random sampling to obtain numerical results. So the first example is probably the most commonly used one for an introduction into Monte Carlo, the Monte Carlo method. And so what we're going to try to do is we're going to try to come up with a way of computing the value of pi. And so one easy way to think about this is just, let's imagine you had a bucket, and your bucket happens to be square, and it has, let me see if I can make it a little more square. So we're going to have a square bucket. And what we're going to do is we're going to say that the bucket has sides of length, let's say 2a. So this is 2a, and this is 2a. So we're looking down at the top of the bucket. And inside of that bucket, we're going to put in a cylindrical bucket, so it has a circular cross-section. And we're going to imagine that the walls of the buckets are very thin, so they're negligible thickness of the walls. Okay, and so this circular bucket has a radius of a. And it's raining one day, and you put these buckets out in the rain. And what you first do is you measure the mass of all of the water in the bucket, so the total mass. And so this is total mass of all water contained by both buckets. And then you measure the mass of the water in the circular bucket. Mass of water in the circular bucket. So what you would think is that if you had a single raindrop fall onto these buckets, you could calculate the probability that it lands within the circular one. And so the probability of landing in the circular bucket, which I'm going to call pH, this is going to be a hit, is going to be the area of the circular bucket divided by the area of the square bucket, which is going to be pi a squared over, let's see, we have 2a squared, which is going to be pi over 4. But when we compare the masses of the water in the circular bucket to the total mass, that ratio is also just equal to the probability of a water droplet landing within the circular one. It's a measurement of that probability. So this is a measurement of this probability of a hit, so the water droplet landing within the circular bucket, and this is a calculation of the probability of a hit. As long as we collected lots of rain droplets, like many rain droplets, then our measured value of this probability should be very good, right? It may not be accurate for just a few little drops of rain, but if we had thousands of drops of rain, then that measurement should be pretty accurate. And we could say, well, it must be the case that pi over 4, our calculated probability, should approach the measured probability in the limit of collecting a lot of droplets. And so then what we could do is we could use these measured masses to calculate the value of pi. So in the Monte Carlo method, we're going to do the same thing, but instead of making it rain water, we're going to make it rain simulated points in a grid. So let's assume that we can produce random numbers uniformly drawn from the interval -1 to 1. Okay, and so what we're going to do is we're going to have x, y, and this is going to be +1 over here. Over here we're going to have -1, +1, and -1. Okay, and so that's our square, and that's our square bucket that we had in the rain. Okay, then we repeatedly draw sample points, say xi, yi, for I is 1 to a very large number, from the interval -1 to +1 on x, and the interval -1 to +1 on y. And then we could say that the probability that a randomly drawn point lands within a circle of radius 1 is, well, that probability is the area of the unit circle of radius 1, divided by the area of our square, which is just pi r squared times 2 times 2, which is this pi over 4 that we calculated for our buckets. So if we go back over here, we can put in our unit circle of radius 1 like so. Okay, so that means what we've successfully done is we could write pi as an expression that involves some kind of probability, and we're going to try to simulate a result for that probability p. So we have expressed our desired quantity pi as a function of a probability. And then we're going to estimate p using a Monte Carlo simulation. So we spray n, where n's a really big number, points onto the square, and the probability that we want is equal to the number of hits, which I'm going to call z, divided by the number of points that we spray, where Zn is the number of points landing within the circle. So I'm going to call this the number of hits. And so that's what Zn represents. And so when you go back here, what we're going to do is we're going to have some points that don't land in the circle, and so we'll call those misses. And so we have these red misses. And then we have some that land within the circle, and so those are the hits. So little n is the total number of points, so red plus green, and z are the green points. Okay, so the hits is the number of green points, and n is the number of green plus the number of red, the total number of points. Okay, so that means that if p is Zn over n and pi is 4p, then we get that pi is equal to 4 Zn over n. Okay, now we could ask also, what is the uncertainty in the value of pi? What we should expect is we should expect that the uncertainty in pi should decrease as n increases. And so let's see if we can work that out. So we're going to have to recall the binomial distribution. So recall the binomial distribution where what it had is a mean was n times p, where n is the number of trials and p is the probability of success. P is the probability of success in any individual trial. And so for us, that's something we could calculate. It's z divided by n. And the uncertainty in the binomial distribution, if you recall, was np1 minus p. That was actually the square of the uncertainty. Okay, so therefore what we have is, in our case, mu is the number of successes, which is z for us. So that means this Zn is equal to n times p. And let's see, the uncertainty in z squared is np1 minus p. And we had that pi was equal to, let's see, what was it? Pi was 4z over n. Okay, so by propagation of errors, what we expect is that the uncertainty in pi should be 4 over n, which are constants, times the uncertainty in z, n. And so that should be equal to 4n. And then we have to take the square root of this. So we have root np1 minus p, which is equal to 4 root p1 minus p. And then we have square root of n divided by n, 1 over root n. So therefore, p is just something we're going to measure through simulation. So we obtain p equals Zn over n via simulation. So that's just a number. And then the uncertainty in pi is proportional to 1 over root n. Therefore, as expected, sigma pi decreases as n increases. So if you want to cut your uncertainty in your determination of pi in half, you have to increase your number of trials by a factor of 4. Okay, and so let me try something here. I'm going to try to show you an implementation of this calculation of pi. And what we have here is some Maple code. And so let's see if I can write on this. So this Maple code here, let's see if I can write on this thing. Tap and hold and drag over. I don't want to highlight. Okay, here we go. So this is generating random numbers. Generating, let's see. Oh, okay. So I'm not that expert at this. Let's write it over here. This is generating random numbers for x and y between 0 and 1. Okay, and so here's a randomly generated number, and then we're going to take over here the square root of x1 squared plus y1 squared, which is the radius. If this radius is less than 1, then that point lies within the circle. And so there it is. If radius is less than 1, then we have a hit. If it's not, then we have a miss. And so this code then goes and calculates the number of hits divided by the number of trials times 4, and that's our estimate of pi. And this was an estimate of pi of 3.12 for n equals 5,000 trials. What this code did is it kept track of hits and misses, and in this case the red were the hits and the blue ones were the misses. If you added up the number of red dots and the number of blue dots, that would be your 5,000 trials. Here the simulation was only done in a quarter of a circle, but that's fine. We don't have to do the full circle. We could just do the first quadrant and get the same results. Okay, so that's calculating pi, and so how could we use that to evaluate integrals? Okay, so let's try Monte Carlo Hit and Miss integration. So let's assume that we want to evaluate the integral f of x from x equals 0 to 1, and we're going to take our f of x equal to, it's some funny function, so it's 1 over 27 minus 65536 x to the 8th plus 262,144 x to the 7 minus 409,600 x to the 6 plus 3,11296 x to the 5th minus 114688 x to the 4th plus 16384 x cubed. So you'll notice this is just a polynomial. We could easily integrate this just analytically, which is kind of an advantage, because what I want to do is I want to see if we can do a Monte Carlo simulation of this integral to get its value, and then we can compare it to the real value that we could easily calculate. Okay, so on the interval x is 0 to 1, this function fits within a unit square. And so if you plotted this, let's see if I can get a reasonable drawing of this thing. So here's x, and here's f of x, and this is going to be 1 over here, and over here we're going to have 1. So if you plotted this function, what it looks like a bit of a trig function here. And so this isn't perfect, but it looks something like this. I can maybe improve it slightly over here. Let's see if I can draw this slightly better. Okay, we'll accept that. And so what we'll do is we'll take some points, and we're going to spray points on this square, and we're going to say if they fall underneath the function, those are going to be our hits. And so those are the green dots. And it's just like the case of pi, we're going to say that the probability of a dot landing under the curve is the area under the curve divided by the total area of the square. And so the misses are going to be these red dots, and so these are misses, and these are hits. Okay, so we use the same raindrop simulation, and the probability that a drop falls below the curve is area under the curve divided by area of the square. Okay, so in general, for our particular case here, the area of the square is 1. But in general, what we would say is that the probability is the area under the curve divided by h times the range. And so what does that mean? Let's suppose we had some other function and it looks like this, okay? It doesn't matter what it looks like. There is some lower limit of integration and an upper limit of integration, and we define some height, which is going to be h. So this is h, and this vertical axis is f of x. So a curve is equal to this area. This is a curve. And h times b minus a is the area of that rectangular box that we drew. But of course, the area under a curve is just exactly what the integral calculates. So that's the integral of f of x divided by h times b minus a. But p, just like for our calculation of pi, is the number of hits divided by the number of trials. And so that means that our integral I is equal to ab f of x dx, which is equal to h times b minus a times Zn over n, or that's hb minus a times this probability. Okay, what about the uncertainty in the integral? The uncertainty in the integral is equal to hb over an times the uncertainty in z. But we saw from our calculation of pi example that from the binomial distribution, the uncertainty in z is root n p1 minus p. And so that's equal to h b minus a root p1 minus p divided by root n. So we had a square root n divided by n. So we get a 1 over root n. And so this is the value of the integral. This is the uncertainty in the integral value. And so this is just like for the calculation of pi, that's proportional to 1 over root n. And p is what we measure in the simulation. Okay, so let's see if I can show you an implementation of this integral for this particular function that we started with. And so I had a bit of trouble loading this, but let's see if we can get this thing to open up. This might take me a second. Let's just see if I can get it to go. Okay, so let's try this. So here is the same thing where we generate random numbers from 0 to 1 for x and y. So those are our raindrops. Here's the function that we defined in the notes. And here's an exact integration of that function. So its exact value, because it's just a polynomial we can calculate, is 0.4816, say. And so there's the plot. Here you can see it sits inside this unit square, so the square has a height of 1 and it has a base of 1. Okay, and then we're going to generate 10,000 points. N equals 10,000. And if the value of the y coordinate is less than the value of the function, then that's a hit. That's something that falls below the curve. Hit. And so what we have to do is, to evaluate this function, we take the x coordinate that was generated, calculate y for that value of x, and compare it to y1. If y1 is less than that calculated value of y, that's a hit. Otherwise, we have a miss. Okay, so I think the A here was like an accept. So we accept that as a hit. And over here, these R's were reject, or hit and miss. Okay, and then what we do is we just take the number of hits. So NOPS is the number of points in the accept list. So that's the number of hits. And I guess this TOP is the total number of trials. Yeah, here we go, TOP. I don't know why I used top, but that's N, the number of trials. Okay, so that's the code, and let me see if I can show you the actual result of the simulation. Let's see if this loads. I'll try one more time. There should be a plot here that shows you the exact function and the hits and the misses. And at the moment, it's not coming up. I'll try a couple more times and then we'll give up. I got it to work once before trying to record. Okay. It doesn't look like it's going to show up. What I'll do is I'll post this to the course website and you can look at it yourself. Actually, there's maybe one thing we can try to do. Let's go to the internet and okay, so that's not working either. Is this thing gonna load? Okay, this is a different version of the same code. There's the function on 0 to 1. Here's the 10,000 trials, and that's what I wanted to show you. Remember, the exact value of this integral was 4816, and the estimated value is 477. So pretty close, 48. And the blue dots are obviously the misses, and the red dots are the hits. Okay, Good. So that's hit and miss integration by the Monte Carlo method, and I'll post those examples on the course website for you. All right. Thanks very much. Bye.